Okay, so hello and welcome to our seventh fall presentation. So again, amidst this remote learning, many robotics students have lost their opportunity to obtain their hands-on experience that they previously had ability to work with. So our team, FTC 14020, Nemesis Prime, um, has been reaching out to professionals, asking to give presentations about themselves, their professional journey, and about a fantastic topic regarding their specific profession.
Today, we have Major Dan Emmons, an assistant professor in the Applied Physics Department of the Air Force Institute of Technology at Wright-Patterson Air Force Base, Ohio. He specializes in plasma chemistry and remote sensing of ionospheric disturbances. Thank you for being here with us, Mr. Emmons.
Thank you for having me. Yeah, really appreciate this opportunity, and it's great to get a chance to speak to some of the younger folks out there and tell them about all the cool opportunities I've had. Okay,
So,
you want me to kick this off, Jeremy?
Yes, go
Oh,
ahead.
sorry, go ahead.
nope, you're
Okay,
fine.
if you don't have any questions. Okay, did you have any questions before I get going, or do you want me to just get started with the presentation?
You can get right into it.
Okay, cool. Well, thanks again for having me. Like I said, my name's Major Dan Emmons. I'm active duty Air Force, but I have a somewhat of a unique job in the Air Force, is that I'm a physicist by trade. So my no kidding job title and what I'm supposed to do on a daily basis is revolving around physics and just technology in general. And I've had a variety of different assignments that I'll go through and talk about to ultimately lead me to where I'm at now as an assistant professor at the Air Force Institute of Technology, which is the Air Force's graduate school. So thanks again, and I've got some nice slides that'll help me talk through some of this. So let me share my screen. Okay, can you see that? Good. Okay. So first off, my topic today is going to be the Earth's ionosphere, but I want to talk a little bit about myself first, and just tell you how I got to where I'm at today, the different opportunities that I've had to kind of get me here, the education that I've needed to go through to get to this point, and then finally the technical topic to discuss is the Earth's ionosphere. And I'm guessing that most of you probably haven't ever heard of the ionosphere. There wouldn't be a strong reason that you necessarily would, unless you knew what it was and why we cared about it. So that's what I'm hoping to impart to you today. Okay. An overview of what we'll talk about. Again, I'll just talk about what I do for my job now as an assistant professor, how I got here, so my career path, a few tips and life lessons. This is more focused on being a student and things that I think will help you as a student, especially when you go to the college levels, right? And the difficulty kind of ramps up. And then we'll talk about the Earth's ionosphere. And this picture on the right, by the way, is a really cool one that we use to describe something called space weather, right? So typically you think of space as this giant vacuum where nothing is really happening, right? And it's just empty space. And in reality, that's not true at all. The sun is constantly spewing out a bunch of material, and it comes towards us, right? And then interacts with the Earth's magnetic field, right? In our atmosphere in a certain way. And you get this really complex dynamic that we obviously care about, right? Just in society as general, because we have all those satellites that we rely so heavily upon. And all those satellites are flying in this region that you would typically think that there was nothing happening at all. And in reality, it's constantly being bombarded with these particles coming from the sun. So this field of study is called space weather, and that's really my specialty, right? I focus on the Earth's ionosphere, which is, you can think of it as the upper layer of the Earth's atmosphere, or alternatively, the first step as you get into space, right? It's like the first entry into space would be the ionosphere. And I really like that diagram because it just shows all the different impacts that the sun would have on things that we care about as a society. Okay, so what do I do for a job? I'm an assistant professor. So just like a professor anywhere, it's the typical professor load. What makes me unique though is I'm active duty Air Force at the same time, right? So I am active duty military. I'm in the Air Force, like I said before. My career field is physicist, which might seem a little strange because you don't typically think of military and then think, oh, they got physicists and engineers and mathematicians and all the like that are walking around. But we definitely do, right? We're especially the Air Force. We're very technology focused and technology based. So we have a strong group of STEM folks that work on these problems and try to constantly increase technology for the Department of Defense. So my current assignment is as assistant professor at the Air Force Institute of Technology. And like I said before, it's kind of the Air Force's graduate school. So it's similar to the Air Force Academy, except the Air Force Academy is kind of this dual-hatted thing where they're on one hand, giving you this education, right? So it's like a normal university when it comes to getting a degree. But on the second hand, they're also training you to be an officer one day. So they're taking somebody who is from a civilian background and they teach them all the skills that they need to know to be a leader and an officer later on. So they're kind of dual-hatted. Where we're at AFIT, we're just a straight up graduate school, right? Obviously, we are very Department of Defense focused because we are through the Air Force, and we're mostly military if you look at the students, but we do have civilians that come in as well, right? So there's no requirement that you have to be associated with the Air Force. It's just, the Air Force is running this, they're sponsoring a lot of the research, and it gives us that strong DoD spin, but it is much different than the Air Force Academy in that you could be a civilian with no affiliation to the Air Force at all and come in and do a master's or a PhD at that. So it's a very unique place. And I am in the engineering physics department, this ENP, where we got a really cool picture of a laser there and somebody doing a neat experiment of some sort. Okay, what do I do as a professor? I do what normal professors do at any university, right? Again, the only real difference is that I'm wearing the uniform, and so I am active duty at the same time. But outside of that, I'm doing anything that a normal professor does. We have students, master's and PhD level, right? We are a graduate school. And we teach classes for one. I teach a lot of the ionosphere courses, one in electrodynamics as well. Those are kind of my core subjects. And then in addition to that, because we're master's and PhD level, everybody has to do a dissertation or a thesis. And so we have to take students in, we have to teach them how to do research, right? Give them the basic skills that they'll need to do this research. And then at the end of it all, we say, here's how you actually write a document to finish this up, right? So here's how you'd write a thesis. Here's how you'd write your dissertation. Here's how you write these academic journal articles that you need to stay alive in the academic realm, right? Things like that. And then, of course, we have to do research ourselves. And that's where the space aspect comes into play for me is my research focus is on the space environment or space weather. And specifically, I do remote sensing of the ionosphere. Please stop me at any time, by the way, if you guys have questions along the way.
I did want to ask Major
Yep.
Emmons, is there a difference between the admissions process to get into AFIT? Because I know for the Air Force Academy, there's a lot of extra steps to take in order to apply. So does AFIT have anything like that?
Not really. No. Thank you for asking that too. That's where that difference between the Air Force Academy kind of having the dual hats, right? And they're training you to be an officer when you come out of there. Where after you don't have to do that, right? You can come in with no affiliation to the Air Force at all, get a master's or PhD, and then leave with no commitment or affiliation to the Air Force after that, right? So it's more like a typical graduate school. So no, it would be very similar to just applying to a normal graduate school and trying to get in that way. Yeah.
Okay, thank you.
Yeah, sure. It's one of those small schools, right? You probably never heard about if you don't have an affiliation to the military. But it really is a good opportunity for civilians that say you're just interested in the DoD and their research, but you maybe never wanted to go active duty for some reason. You can still come through and contribute in a different way like this, and this is a really good opportunity for that. And I like to think it's a great school too, so I'll plug it. Maybe I'm biased. I don't know. Okay, so what do I do for research? I'm doing remote sensing of the ionosphere, right? So there's a lot of different aspects to what we're looking for, and in general, maybe this is slightly out of order because I haven't told you what the ionosphere is yet, right? But the ionosphere is that outer layer of the Earth's atmosphere that's ionized. So it's ionized. That means you create this plasma, and then plasmas interact with radio waves, right? So that's why we care about it as a Department of Defense. We want to know if the ionosphere is doing something funny, if it has some sort of a disturbance or something like that. And so what I study is this disturbance called sporadic E, which is you get these meteor deposits. They come in, right? The meteors, they get ablated, and they leave some of that heavy material around. That material ends up getting ionized by solar radiation, and then it can sometimes get sandwiched together through these wind shears and create these really strong layers that typically wouldn't be there. So that's a picture of it on the left here, right? That really crazy looking pattern. That's actually a measurement of it. And you can see how that's just sticking out above the background, right? You have this really strong plasma cloud that's out there that shouldn't really be there, right? It doesn't fit in with the normal ionospheric profile. So obviously, if something like that happens, it's going to have a pretty big impact on some sort of a radio wave that you might send through there. And we would like to not only know where that's occurring and when it's occurring, but how well can we characterize it if we actually do measure it, right? So it's kind of a two-pronged approach. So on one hand, we go in and we actually look at the data. You can measure it by the ground. There's these thing called ionosons, where you just sweep through a bunch of different frequencies and measure how long it takes for them to go up, bounce off the ionosphere, and then come back down, right? And from that time of flight info, you can build this really cool profile about what's going on overhead. And you do a few math tricks in there, and you do this inversion technique to give you this electron density profile, which is this black background there. So that's one way you can measure it. Those are great, but you don't have those. We have maybe 30, 40 of them throughout the globe, right? So there's not a ton of them. There's a decent amount, and they do a really good job. But there's also places like in the middle of the ocean that you just can't measure with these. So you have to do something that's satellite based instead. And we use this technique called radio occultation. So it's a satellite to satellite measurement. You got something like GPS that's constantly transmitting these signals, and that goes through, right? It travels through the ionosphere, atmosphere, and then we measure that GPS signal at some low Earth orbit satellite, like these cosmic satellites. It's a cosmic constellation. And from that, what happens is that as this signal is going through the atmosphere, ionosphere, it gets perturbed by whatever's there, right? And as it's perturbed, you can measure it, and then you do this essentially this inverted problem. You say, boy, I got this really funny looking thing on my measurement. What would have caused that? And you go back and try to figure out what it could have gone through that would cause it to give you a signal that looks like it does. So that's one hand, right? You actually look at the measurements and you try to make sense of it. The other approach is you try to model it, and you say, you know what, it's tough to do that. It's this inverted problem. It's tough to go back and find out exactly what I went through. But what I can do is if I do the modeling approach, I can completely control what I'm going through and then look at the patterns that it produces at the end. And so that's what this picture on the right hand side is. That is us modeling a GPS plane wave that comes in. It gets perturbed by some layer that we added here at 0, 0. right? We add some just a plasma enhancement there. And then what that does is it acts like this negative lens, and this negative lens is pushing the energy out from either side. So as it propagates the rest of this 3,000 kilometer distance, which is essentially this point that it crosses to this LEO satellite there, we can look at what that pattern looks like on this right hand edge there, right? And that will tell us what to expect when we're actually measuring it with this other satellite. And to get into some of the math of this real quick, I was told that I can, so I will. Right? If we're going to measure and talk about how does a wave propagate, you can start from the wave equation, right? In electromagnetics, you can actually get a wave equation, and if you convert that wave equation to a spatial dependence, you do a few things, right? And then what you get is you get the Laplacian plus the wave number squared times the index of refraction squared times this u, where this u is essentially the amplitude of your wave, right? And then you got a phase piece that you're multiplying your amplitude by. That's kind of removing some of the quick variation in that direction of travel, right? So the Helmholtz wave equation, you take that and you can do some approximations. Well, first thing, you just expand it out, right? You expand that Laplacian. So it's the partial with respect to x, right? Plus z, we're just doing a two-dimensional thing here. And then you take the derivatives, you've also got an x up here in the phase that you have to account for. So when you go ahead and take all those derivatives, right, and expand it, you get this middle equation here. And then from this, we can make these additional assumptions and say, you know what, this second derivative term with respect to x, right, the direction of propagation is going to be pretty small for certain scenarios. So I'm going to drop that. And when you do that, you get something called this parabolic wave equation. And what's really nice about that is it's second order in z, right? So if you're going to solve this computationally, that means you need a boundary on the top and the bottom to solve that, right? It's second order, so you need two boundary conditions. But if you look in the x direction, it's first order derivative, right? Del x u, right? So del u del x, which means that all you have to do is give it an initial condition on the left. And once you give it that initial condition, then you can just do this marching solution where you just march through, march through, march through, march through, march through until you get to the very end, which makes it much more computationally inexpensive than trying to solve the Helmholtz equation, which is second order in both directions. And you need to solve for that entire grid for every time step, and it'd be much tougher to do. So for these really long distance calculations that we do, that parabolic wave approach is fairly standard, just because it would be so computationally expensive to try to solve the full wave equation in all its glory. Okay, so that's what I'm working on. More to come on the ionosphere. Okay, career path. How did I get here, right? What did I do to get myself at AFIT as an assistant professor, right? It's kind of a strange career path that led me here, but let me walk you through it, right? First off, I did Air Force ROTC at San Diego State, right? So I graduated high school, went off to the university, knew that I wanted to do something with the military, right? That I grew up in a military family, so I was always interested in that. And I saw that the Air Force had this really cool opportunity, and they were very technically focused. So I said, well, let's go for that. So I did Air Force ROTC at San Diego State Detachment 075. That's the picture on the right. And that's where I did that training. So it's kind of like the Air Force Academy and how I was talking about they train you to be an officer. ROTC is the same thing, except you're doing it at a normal university, right? So you go in, you're a civilian most of the time, but then you do some of your Air Force training along the way. And then in the end, you end up in the same place, right? You end up being an Air Force officer either way you go. But for me, the ROTC option was much more appealing, right? I kind of wanted to have a quasi normal college life, and wanted to go stay closer to home, which is California for myself, anyways. And while I was there, I studied physics with Dr. Anderson here. He was my advisor. And I had an emphasis in lasers and optics. So I went more down the lasers optics route to start off. And we actually did a really cool senior project on ultra fast lasers, which I don't know if you've ever heard of those, but they're also called femtosecond lasers. So they're these laser pulses that are really, really small in time, right? They push them down to femtoseconds, so 10 to the minus 15, right, second pulses. And you do these really cool tricks to get them that small. But when you do that, they have this enormous amount of power because it's over such a small amount of time, right? And you can do these really neat things with it. So it's a great project. Love the lasers and optics side of it. Enjoyed the ROTC, right? And then I graduated and I got my commission and I was active duty after that. So typically when you go into and if you do join, they look at your background, they say, okay, what was your background in, right? What did you study? Where should we push you? What sort of job should we give you? I had the physics background, so I wanted to do a physics related job. And that's what happened as I graduated. They said, you're going to be a physicist for the Air Force, and your first assignment is going to be at the Air Force Research Laboratory in San Antonio, Texas. So there's a bunch of different places that have AFRL, right? Air Force Research Laboratory. I just happened to go to San Antonio, Texas as my first assignment. And that was the Human Effectiveness Directorate. And we were in the Directed Energy Division. So we looked at things like high energy lasers, right? So one of them is this advanced tactical laser that you see in the picture on the left-hand side. And that was, they put a really high energy laser on a C-130, right? And we're flying it around and hoping to do some shots from it. So it was really cool to be a part of that. And then, of course, as part of this, right, we're saying if we start using these high energy laser weapon systems, it's so new, we got to look at these collateral hazards, right? So they're going to hit things like something metallic, like in this picture here, and they're going to burn it, right? And then they're going to reflect off of it. So what would happen if somebody was standing nearby, right? And so it's questions like that that you have to answer. And that's the sort of stuff that we looked at when I was at AFRL in San Antonio. It was really cool. It was a really unique opportunity for somebody coming out with only an undergrad and a degree, right? Typically, if you come out into the normal industry and some of the STEM fields, it depends on what you're in, right? Computer science is different. Some of the engineering is different. But if it's a hard science like math and physics, it's tougher to come out with a bachelor's and go right into, some of these jobs in the industry. Usually they want like master's, PhD level before you can kind of get your foot in the door. But for us, it was neat as I walked in with a bachelor's and I got to work with all these PhD level researchers on these really, really cool research topics. That for me, I learned so many different research skills while I was there, that it was very appealing, and it just made me want to go further in my academic studies. So after this assignment, they said, "Hey, you want to stick around and go get a master's degree?" And I said, "Sure, of course I'll do that." Yeah, so they sent me to the Air Force Institute of Technology, where I'm teaching now, right, to get a master's degree. And this was a full-time assignment for us. So it's one of the really cool benefits that we get is they'll send us full-time for master's and for PhD, as you'll see here in a second. Where my full-time job was to be a student, right, in one of these STEM fields. For me, it was applied physics, and I got to go work on my master's degree for a year and a half while I'm active duty. So it was amazing opportunity. And when I got sent there, they said, "Here's your list of potential topics that you can choose," and one of them was in space physics. And I've always been interested in space. So when I saw that, I said, I have got to give that a shot, right? Like this is for sure me. Even though I was more of an optics guy before, when I saw this, I said, I have got to do that. So I worked with my advisor, Ariel Osabal, who was amazing. And we did this thesis project on ensemble forecasting of coronal mass ejections, right? So what is a coronal mass ejection? That's what these pictures here on the right hand side are, right? What it is the outer portion of the sun, the corona, occasionally will have these huge eruptions and releases of energy, where it's usually accompanied with a solar flare, right? But you get this massive ejection of mass from the sun from these explosions, right? And here's a couple pictures of them. In this inner white circle there, that's the sun, right? It's just blocked out so you can see what's going on like during a solar eclipse. But that circle there is the sun. So you can see how gigantic this stuff is that's getting shot out from the sun. So one of these coronal mass ejections, CMEs, happens, and it shoots off something like 10 to the 12 kilograms of material into space, right? And obviously, if that's headed towards us, which it does occasionally, we want to know about that. We want to know how long it's going to take before it hits us, because once it hits us, it can have all sorts of effects on our, our magnetosphere. It can actually change the magnetic field that we measure on the Earth's surface. And I don't know if you're familiar with Faraday's law, right? But if you have a time-changing magnetic field, you're going to get an electric field that's produced that tries to counter that, right? So we care about that on a global scale because of the power grids. If you get a big enough change in the magnetic field measured at the Earth, right? If you look at the flux of that and it's this big change, that can actually destroy some of our power grids. It's big enough to do that. So we actually have to be able to forecast when these are going to hit, and then we have to contact the electric companies and say, hey, get ready. You got to be prepared. You might see this giant surge because this thing's about to hit us. So really neat stuff, right? I absolutely love the space side of things, and I was very fortunate to be able to do that. Okay, so then I got my master's, right? Got the master's, and then I went back to the Air Force Research Labs again. But this time I went to Albuquerque, New Mexico. And there it was I was fortunate that it was also a space related project, but this time it was more on the ionosphere than it was solar, right? So it's this outer layer of the Earth's atmosphere that you can kind of see in this diagram on the lower right hand side, right? The sun comes in, it does this process called photoionization. We'll talk about that in a second. And it creates this plasma on the outer portion of the Earth's atmosphere. And we care about that because we are constantly communicating back and forth with satellites, right? And if you have this thing that is interacting with your radio waves that you're using to communicate with your satellites, and something is impacting that, you would want to know about that, right? We need to know that something funny is happening with this signal and that I can't reach my satellite, or my signal is just going to be all jarbled for some reason. So that is why we care about the ionosphere, right? One of the big reasons. And this picture on the upper left is a rocket launch where we went to the Marshall Islands, which is way out in the middle of the Pacific, and we released this samarium, which is one of the elements, right, on the periodic table. But we released this samarium into the atmosphere, and it created this artificial plasma cloud, which you can see here. It's that bright red spot there. So we launched this rocket, it released this stuff, created this artificial plasma cloud. And that was maybe the coolest thing that I've ever done, just in general, like being a part of that. I stayed on this little island called Wotho, which we had to bring in all of our own food. We had to bring in all of our own water, all of our own gas to run a generator, right? Because they had no running water, they had no electricity. I mean, it's this little tiny island out in the middle of the Pacific where we got to go in and essentially camp out there for about a month doing this experiment. Yeah, so just getting to see how people live, in places like that, and the locals were all amazing, really nice, friendly people. But just seeing that different lifestyle, right, and getting these opportunities that I never thought I would have done something like that, right? I mean, I've just been so fortunate along the way, and plus we were doing this really cool science at the same time. So it was to actually see that in person. That the picture doesn't do it justice. But when it's pitch black out there and that thing went off, it was pretty cool to see. Yeah, and it didn't hurt anybody either. So please don't think that, right? It was, yeah, harmless. Okay, so after that assignment at AFRL again, they said, "Hey, you're still around. You want to go back for a PhD?" I said, "Absolutely, yeah, please." Right? And so they sent me back to AFIT for the PhD in applied physics. And there I switched gears slightly. It wasn't a space related topic, but it was a really cool one on something called an optically pumped rare gas laser, right? And so it's trying to make this next generation laser system. And what was neat about this one is you actually had to make a plasma as the laser medium. So that's what these pictures are in the lower left and upper right, right? We create this laboratory plasma with a rare gas. So something like helium, right? Argon, You take those and you make them into a plasma, and then you use this first excited state of these different atoms as the ground state of this laser system. So what we had to do is try to model and say, okay, well, how much of this ground state or this first excited state is going to be around, as a function of pressure, composition. Maybe we give more voltage to it and see what happens there. And we were trying to predict if we can get enough densities to make this a really high-powered system, right? So it was a really cool project. That's where I learned how to do plasma chemistry, right, and became much more familiar with plasmas in general. And then obviously I got to learn these really cool research skills while I'm working on a PhD degree, all while I'm active duty at the same time, right? So it was just amazing opportunity. And then once I did that, I just stayed here. So I got my PhD at AFIT. I stayed at AFIT, which is kind of a strange thing, but we do that because we're military, right? And they give us this opportunity to actually teach at that organization once you get your PhD. And so that's where I'm at now. Right. So labs, AFIT, and I'm just staying at AFIT as long as they'll let me because I absolutely love it. Okay.
We have a few questions here, Major Emmons.
Please, yeah.
You mentioned some interesting experiments you were able to perform with some of the lasers that you worked with at AFIT. Could you give any examples of those?
Like this one here.
Yes.
Yeah. So what I did on this portion of it was more of the modeling side. I didn't really do much on the experimental side, and this one we were more of trying to make the medium for this laser than actually the next step would be once you've got the medium, right, which is what's given the laser its energy to amplify it. But once you got the medium sorted out, you can make it into a laser and start doing laser diagnostics. But we were at the very, very initial step, right? There was another group that went out that said, hey, we can actually make this work, but here's what it relies on, right? It relies on this. If you look at the color bar here, this AR1S5, right? That's the first excited state of argon. So my goal was to try to model how much of that metastable state, they call it, of argon we could get as a function of all these different parameters. So this was much more computationally, I'd go in, I had this whole chemistry package and I tried to solve it for all these various conditions. So even though the end goal was a laser, what I did was much more of a chemistry problem almost, and it was a computational chemistry problem at that. But we do a lot of laser research at AFIT. I just didn't do much of it really at all for my degree. And I kind of did that on purpose because I knew I was going to go back to the space realm afterwards. So I wanted to do a topic that was as close as I possibly could to staying in that space, computational plasma realm. And so this one popped up, and I said, yeah, that's perfect.
On the topic of lasers, when you mentioned working on directed energy weapons and attaching them to, I believe, a C-130, we had a question about what were some of the hazards that you could have run into while working on a project and working with these lasers.
Yeah, great question, right? One of the obvious ones is we know that there's a limit for eye safety, right? And we know fairly well what those limits are as a function of wavelength and laser system. And so there's actually a book that you can look up, and it'll give you calculations to say, hey, if you're using this particular laser with this wavelength, then is it pulsed or continuous wave, right? Then here's the threshold that you need before you're going to be in danger. So that was the big one, right? And that still is for a laser weapon is you don't want to accidentally blind somebody like an innocent bystander standing by, obviously, right? That'd be horrible. So we want to know that, hey, if this thing is reflecting off of a material, what does that reflection pattern look like? And then we go compare that to these eye standards essentially and say, did we meet the threshold or not? So that would be the most obvious one that pops out. Yeah.
And then kind of a two-parter. You mentioned coronal mass ejections from the sun and how they can affect power grids. Do
Yep.
we know what causes coronal mass ejections? As well as how often is it that you need to kind of alert electric companies about any potential effects from them?
Yeah, all great questions. So what causes them is you get these really complex magnetic structures on the surface of the sun. And there's actually, it's something called the solar cycle, right? It's every 11 years we go through this maximum minimum of solar activity. And that solar activity is related to the magnetic field complexity on the surface of the sun. So these things called sunspots start to form, right? They're these dark areas of the sun. And if you're looking at it and it's got this really dark, complex looking magnetic field, what that does is it stores up a bunch of magnetic energy. And if the conditions are just right, that magnetic energy can be released. And when it's released, you get things like solar flares, coronal mass ejections. So it's a release of this magnetic energy on the surface of the sun, which is really strange, right? You don't usually think of magnetic fields, right, as carrying all this energy. But in reality, you look at something like the sun and they absolutely are. How often do we have to care about that? It's usually during the solar max, right? That's when you would expect those. So for us, we're in a solar minimum right now. The chances are very low something like this would happen. But let's fast forward to 2025 is when the projected next maximum is. Then we got to start worrying about this, right? And this is something that as our society starts building more and more satellites and relying more and more on satellites, right, and space in general, things like this are something that we definitely have to keep an eye on. Now, how bad, does it have to be to really cause damage to the power lines and stuff like that? That's not as often, right? There's got to be a big eruption. It's got to be geo-effective, so it's got to hit us right on the Earth, right? The conditions, the configuration of its own magnetic field with respect to the Earth's magnetic field come into play, right? So there's a bunch of different factors that come in, but I want to say the last big one that we had was maybe 2003 or something like that. So it wasn't too long ago. And certainly, anytime something like this comes at us, we do need to be cautious of it, right? Just in case. So we'll have to see how bad this next solar maximum is, but this is something we're absolutely going to be keeping our eye on. So 2025, watch out for that one. Yeah. Okay. Okay. Let me give you some quick tips. Right. Again, this is much more geared towards um, being a college student. And the big one that I wanted to say was just college is going to be tough, right? You go in there. Most people come in, they've done really well in high school. Maybe it was easy for you, right? And you walked in and you just got everything. And like, oh, it wasn't a problem at all. And then you get to college and they just ramp up that difficulty significantly. So if you're used to just getting everything right away and school being relatively easy, and then you go to college and it becomes tough, right? Don't get discouraged. Just know that that's completely normal, right? And there's a very small group that walks into college and is just like, oh yeah, this is all easy. Like I got it, right? That's a very small percentage of everybody else. Everybody else comes in and it's just, wow, that's tough. It's tougher than I thought, right? I don't get it right away, but it just means you got to spend more time and effort trying to understand it, right? But just don't think that like, oh, I'm too dumb to do this, right? That's not it at all. You just got to spend the time and effort to actually slog through it and learn it. So don't get discouraged if it's not easy. Join a club or a team or something, right? If you only do school and that's all you think about all day long, you just kind of become one dimensional, right? Plus, it's easy to get burnt out if that's the only thing that you got going on for you. So be social, right? Join something else, get your mind off of school for a little bit, give yourself a mental break. And it's good to have a mixture like that. And I found out that one the hard way as well, right? Just only focusing on school and you get to a point where you're like, I got to do something else, right? It's good for your own mental health, mental sanity to have something else besides school. And then, of course, you got to take time off to rest. So if you think, hey, I'm going to go in, take a full load in college, I'm going to work full time and join 10 different clubs, and the only way that you can do that is by working 7 days a week. It might last for a little bit, right? But you are certainly going to hit a point where you're going to get burnt out, and then nothing's going to make sense anymore, and you're just going to stop enjoying everything that you have. And I can tell you this one from my own personal experience again. I tried to go, especially when I came back for the PhD program. I was like, I'm going to go 7 days a week, right, and just get more work done that way. And it was good for maybe a few months, and then I got burnt out, and it was this diminishing return, where by working more, I was actually getting less done overall because I just couldn't think straight, right? It was a quick burnout. So don't do that, right? You got to have a rest. You got to give yourself a mental break, and just have an overall life balance with all these. And then I'd say, when looking for a degree, instead of saying I'm interested in something, I'm going to go study that, which isn't bad. But I think a better way to do it is to say, what job do I want, right? And then once you know what job you want or what career you want, then you backtrack and find out what you need to do to get to that job. Right. So if you want to be a teacher in a certain subject, you got to go in, get at least a bachelor's, someplace even master's, right? Get a teaching certificate in that particular field, right? You want to go do something like industry, physics, or math, you're probably going to have to go all the way through a PhD, right? That's just what it's going to be. If you want to work at Google, say, right, you probably want to go do a computer science or computer engineering degree, right? It's all about where you want to go, and then it's easier to backtrack and find out what you need to do to get to that place that you want to be. And I think that's kind of backwards from the way a lot of people do it, right? And it's easier to run into trouble if you're not thinking ahead of what you want to do. And I know that's tough sometimes because you might not know, right? That was certainly my case. I didn't know exactly what I wanted to do, and I was like, oh, I think physics is really cool, so I'll do that. And I think I got kind of lucky. It kind of all worked out for me, but I've also seen the other side of that as well. So yeah, tips for success. Okay, let me switch gears to the ionosphere finally.
Before we do, we have
Yes,
a question from one of our viewers on
please.
YouTube Live.
Yep.
They're asking if a solar maximum could potentially cause solar panels to become more effective. Um,
Um, I'm not extremely familiar with solar panels, to be honest with you. So when I say that, I don't know which wavelengths they're using to gain their energy. Um, if they are using UV, right, or some of the higher frequency ones, then there will be a change in those. Although I suspect that's probably not the case, that they're probably tuned to something more along the lines of a visible wavelengths. And if that's the case, that visible part of the solar spectrum stays mostly constant, right? Like you don't really see much of a change in that at all. It's only the extreme edges. Actually, I got a slide on it in a couple from here. It's only the extreme ultraviolet, right? So the high frequency stuff or the low frequency radio wave that shows a really strong solar cycle dependence. The visible part stays pretty much the same no matter what the solar cycle is doing. It's because it's produced at a different part of the sun that isn't really showing this same fluctuation. Yeah, great question. I would say if it's in the visible, probably not, right? Probably not. Or if it is, it's going to be very minor. Okay, my son's in here in case you hear something. Okay, let's go to the Earth's ionosphere. So the ionosphere, oh, can you hear that? Hey, pals. Thanks for your help. The Earth's ionosphere is the upper portion of the Earth's atmosphere that actually gets ionized by solar radiation, right? So the sun comes in and it's those extreme ultraviolet or even X-ray wavelengths that comes in, and it through this process called photoionization actually will rip off these electrons from the neutrals and create this plasma. So when we think of this, right, we typically think of the aurora because that is part of the ionosphere, even though that's produced by particle precipitation more often than not. That's related to this whole part that the sun, right, is interacting with the upper portion of the Earth's atmosphere and it's doing something to it. So on this right-hand side, you can see that we've got these different layers, right? If you just look at as a function of altitude for a typical part of the Earth's atmosphere, on the very lower portion, you've got the troposphere, right? That's where we live. Down here below, like 10 kilometers, right? You got the plains are going, the mountains are there, you get clouds and all that. But as you go further and further up, so you get to about 100 kilometers altitude or so, that's where I would say space is starting, right? So that is kind of that entry into space. And that's about where you start to see that ionosphere as well. So that is going to be the region where you're getting a lot of this interaction between the solar radiation and the Earth's atmosphere. Okay, and I've said this one several times throughout, and I'm guessing probably most of you aren't familiar with plasmas, or maybe you've heard and don't know exactly what it is, right? A plasma is where you have a neutral atom, so what we're typically used to thinking of, and you actually, something happens where either it gets hit with something or it absorbs a photon or something like that, and it actually rips an electron off of the neutral one. So now you have a free-floating electron and a free-floating positively charged ion that's floating around as well, right? So it's unusual for a normal gas. It doesn't act like that. A normal gas is all neutrals, but a plasma, you actually have these charges that are produced, and these charges make it interesting because now it's going to respond to these electric and magnetic fields, right? And so that's why we care about these plasmas, is because for us, if we're trying to send a radio wave through it and you've got all these charged particles, they're going to interact with that electric and magnetic field and give you this really strange behavior. And looking at this plot on the left, right, what's a typical, a variety of different things cause plasmas. The ones you're probably most familiar with, right, are going to be lightning. You've got the neon lights, fire, right? You can even get some plasmas in that. And then, of course, the sun. The whole sun is going to be a plasma, right? It's so hot in there that it just can't keep everything together, right? The electrons are pulled off of the neutrals. So you have these ions and electrons that are free floating around, right? And probably no neutrals at all there, or very few, right? If there's any. Okay, so that's a plasma, right? And we care about it because it responds to electric and magnetic fields. And here's the solar spectrum that I was talking about, right? The typical sun, if you look at it, it has a few interesting areas of behavior, right? If you look at the visible, the beginning of the ultraviolet and in the infrared, that behaves like a normal black body curve. That might be a term that you maybe have never heard, but a black body radiation is normal thermal radiation that you would expect from something. So if you have anything that has a specific temperature, it's going to emit some sort of radiation, and it follows a very well-defined curve when it does that, right? And it looks like this, right? It kind of goes up, right, peaks, and then it drops off exponentially after that. So for us, the normal portion of the sun is behaving like this black body curve, where the visible part is actually the peak of the spectrum that's coming from the sun, right? And by the way, the units here are a spectral radiance, right? So it's a flux. It's a number of photons essentially per unit area per unit time. So how many photons are emitted by the sun? So it's nice for us, right? And we've probably adapted to be sensitive to the visible part of the spectrum because that is the peak part that's coming out from the sun, right? So our eye is tuned into that, right? Which makes sense. But now if you look at the extreme ultraviolet X-ray portion, so as the frequency goes up to the left, this is where you see a lot of interesting behavior over the solar cycle. This portion here, not changing very much. This portion here changes a lot, right? Because as that magnetic activity starts to change, you start to get more and more interactions that are producing this radiation and these photons with this really high energy. And why do we care about this part of it? because that's the part that actually comes in and does this photoionization, right? It's that EUV, extreme ultraviolet, and X-ray photons that will come in and actually be absorbed by an atom, right? That's what this picture is showing you. This photon with frequency nu comes in, it is absorbed by this atom, and it actually rips off an electron, right? It's got so much energy that when it's absorbed, it spits off this electron from that atom. And now you have a free floating electron and a free floating positively charged ion there as well, right? And that process is called photoionization. And of course, like everything else in physics, there's a conservation of energy and momentum that comes into play. So how well is it going to be absorbed, right? What's the frequency? It also depends on what's absorbing. So if you look at this plot on the left, right, as a function of altitude, this is telling you where the most amount of that radiation is being absorbed. And it depends on very much on what the particles are. So is it nitrogen? Is it diatomic nitrogen, right? The N2? Is it atomic oxygen? It can be O2, right? The molecular oxygen. It can be any one of those, right? And it really has this strong dependence not only on the background, but also on the altitude as well, right? And the frequency of that light that's coming in. So the stuff that's below about 100 nanometers there, that's your EUV and X-ray portions of this that's causing most of this photoionization. And look where it's being deposited, right? 100 to 150 kilometers or so. Okay, so it's produced, right? We produce this plasma on the outer portion of our Earth's atmosphere, right, through this photoionization and particle precipitation, but I don't want to get into that, right? Mostly photoionization. And then the question is, well, how do we actually measure this, right? It's this plasma that's like 100 kilometers or more up in the sky. We can't just look at it like we look at a cloud and say, oh, there's a nice cloud of plasma there, right? It doesn't work like that. We wouldn't be able to see it. So we have to do these indirect ways of measuring it. And most of them involve sending a radio wave either up to it and looking at the reflection coming back down, or looking at radio waves that are just propagating through it in general with something like GPS, right? So on the right here is info taken from GPS signals that are going through, right? We call this a signal of opportunity that's just constantly transmitting. We can measure them down here, and we look at the different frequencies that are being transmitted. And if we can play some tricks by looking at the phase differences between those two, and from that we can do a little bit of math and estimate this parameter called the total electron content, which is essentially an integrated value of how many electrons you went through along that path. And what's neat about that is if you have this really dense network like they have in Japan, which they're great at this, by the way. Japan is awesome with ionosphere research. You actually have such a dense network that you can look at these waves that come through in the ionosphere. So these things called traveling ionospheric disturbances, which are waves that are produced in the ionosphere. They're also in the neutral atmosphere, but it's the manifestation of those in the ionosphere. And you can measure them using this GPS, right? You can clearly see some sort of wave-like pattern that's produced by this perturbation that happens. So things like earthquakes, tsunamis, right? Things that shake the ground and that ultimately goes and maps up to the ionosphere, those will produce these traveling ionospheric disturbances. So really cool things, but we care about those, obviously. If this is happening overhead, we want to know about it. And then you've got these things called incoherent scatter radars. So those are great, right? They're amazing. You get a ton of information on it, like a temperature, the motion of the particles, the densities, but look how big that is, right? That thing is gigantic. We only have like a handful of these across the globe, right? They're huge, they're expensive, hard to operate. Yes, they are the best thing for measuring the ionosphere, but they're also a lot to do, right? It's not an easy thing to build and to operate. Obviously, by doing something in situ, right? So in place, like having a sensor in a satellite that's flying around is ideal, right? Anytime you can actually go into something and measure it in that position, that's the best, right? So this is a measurement device that's placed on the International Space Station, the ISS, that floats around and actually measures the ionosphere while it's doing that. right? So that's kind of your optimal measurement. Now the problem with that is obviously you have to be at a particular altitude, right? It depends on the orbit of these satellites, and you're not sampling across the entire globe at all the altitude ranges that we would want, because it would just be impossible. You'd need too many satellites to do it. So it's a great way of doing it, a great measurement source, maybe the best way of getting an actual in-place measurement. But you can't use that to cover the entire globe and do all those measurements, right? There's just not enough satellites to do it. And over here, we've got an optical technique called an all-sky imager, where it's essentially just a camera. You put a filter, you put a fisheye lens on the camera, you put a filter on it, so you're only looking at one particular wavelength, and you're looking for this phenomenon called air glow, right? So as these excited electrons, ions start to recombine, they go to these excited states, right, as a neutral, and then over a certain amount of time, they're going to decay to a lower state and emit a photon when they do that. And when they do that, it's called this spontaneous emission, right? When they spontaneously emit these photons, if we look at it over a long enough time, we can actually collect these photons that are coming in and get an idea of what's going on overhead, right? So this one, I sometimes I even do this in the visible, but it's so faint that even at night you wouldn't be able to see it with your eye. You need a camera to stay on and do like a longer integration time to actually see the patterns. But when you do, you can see, right, that all of this is going to be related to the number density of electrons that are there, right, at a particular time. So you can go and just look at it and see this structure, right? Like, look at this really cool structure. And that one is from a plasma bubble that's created there, right? So you create these plasma bubbles, and it gives you these really complicated patterns that you can see with this camera. And then obviously we got the radio occultation and that sounder that I had talked about at the beginning of the presentation as well. So it's a tough thing to measure, but right, we got to do it. And that's what's given me a job right now, essentially, is figuring out ways to improve the measurement techniques that we have. And finally, why do we care about this, right? Like, why do we care about the ionosphere in the first place? I'd already kind of mentioned this, but here's a couple better diagrams to display this. If you are communicating to and from a satellite and everything is nice and calm in the ionosphere, that signal is going to come through. It's going to be unperturbed, right? It's going to be nice and clean. You're going to be able to communicate with that satellite, no problem. But now imagine that you have like a large perturbation, like a bubble here, right? And that bubble forms and you're sending the signal through. Well, what happens to that signal now when it's down here at this thing that you're trying to measure? It's going to be all jarbled, right? It's going to be degraded. You may or may not be able to actually use that signal. So for things like satellite communication or navigation, even like GPS, right? If this is a big enough perturbation, it can throw off your GPS, so your GPS isn't going to be as accurate as it usually is. And obviously for us, right, that can be a big problem. And then two is actually communications, right? So we know that radio waves can reflect and refract off of the ionosphere. So we sometimes will take advantage of that, and you can do these things called like over the horizon communications, right? If I want to talk to somebody very far away cheaply, I build this HF transmitter, right? And it can actually go up, sends a signal up, it bounces off the ionosphere, and then goes much further than it would by just a normal line of sight. So that's a really common, cheap way of doing communications that people have known about for a relatively long amount of time. And what's nice about that one is if you know what the ionosphere is doing, right, you can pick the optimal frequency and know that your signal is going to get wherever it's got to go, right? And again, if something funny is happening, you get some sort of a bubble or something like that, obviously that final signal is just going to be really degraded, maybe even unusable, right? So for us, the communications, I think somebody's liking this one. You get the communications, right, and the navigation and timing are the big things that we really care about, and why we need to know what the ionosphere is doing at any given time, ideally across the entire globe, which is a really tough problem to do. Okay, that was it. And any questions? I know that was a lot there.
We have a few more here.
Okay, good.
So, what are the ways that you can reduce the disturbance that the ionosphere causes with telecommunications?
Yeah, it's a tough one for things like those plasma bubbles, right? We have this thing that they're called equatorial plasma bubbles, if you want to look it up. But near the Earth's magnetic equator, right? This is a geomagnetic phenomenon. Um, you get these instabilities that form almost every evening, right? And they produce these giant bubbles. So if that's happening, there's other techniques you can use. It turns out one of the easiest ones is that the index of refraction of a plasma, right? So how it responds to light is dependent on the frequency of the signal. So the higher the frequency of the signal, the less of an impact that index of refraction is going to have. So if you're able to adjust your frequency of the signal, which some things can, right, then you go to a higher frequency that's going to be less perturbed by that plasma in the first place. That's why things like GPS are at a relatively high frequency, so their perturbation is usually relatively small, although it does happen. But for the most part, they're usually safe. It's the stuff that goes lower and lower. So if you're like hundreds of megahertz, that those can be impacted fairly strongly. So if you can't change your frequency, that there's not a whole bunch you can do, but maybe wait, right? It can be that bad, right? And again, this only happens in certain places of the globe at certain times. But that other experiment I had talked about where we released that samarium cloud, that was kind of an idea of like maybe if you can control this, right, and release something into the atmosphere that actually adjusts it, then maybe you can kind of short circuit that instability and flatten it all out and get everything calm again. But that's tough to do, right? Like realistically.
And last question here, other than the fields that you covered in your presentation, what are some other jobs that somebody who majored in physics could have been assigned to at the Air Force?
Oh, there's a lot. Boy, there are a lot. And just in general, in the Air Force, DoD, we do a bunch of different areas of research. Pretty much, well, I shouldn't say most of the ones you can think of, right? Um, Optics is a big one. Computers, computer science, the whole um, quantum computing, right? That's a big one. Um, Boy, yeah, there's space. Obviously, that's what I've been doing. Um, there's more just regular directed energy, right? So looking at lasers, how lasers interact with things. There's propulsions, right? So how do you make better rockets or propulsion systems for satellites and things like that? Sensors is a big one, right? You've got can you improve sensors or maybe sense something that you couldn't usually make a sensor for in the past. I'm trying to think of more. There's, of course, like antennas, like developing antennas, improving that, improving just propagation through things. Of course, there's still like the nuclear detection, right? So can you detect somebody that happened to set off something? That's still a field that we care very much about, obviously. Boy, I'm sure there's more, but I'm kind of blanking. There's just a ton, right? If you're really interested in that one, I'd say look up Air Force Research Labs online, and they have all their different directorates listed out and some of the different areas that they work on. And you'd be surprised. I mean, there is a lot, and not only for us, Department of Defense, right, but also look at somebody like the Department of Energy, who are the ones that are running the national labs, right? So Sandia, Lawrence Livermore, Los Alamos, they're doing a ton of really cool research as well, and I would look into them.
It's awesome. Do you have anything else for us?
Boy, no, I just want to say thank you again for giving me this opportunity. It's great to talk to some other folks that might be interested, and you can look me up anytime, right? My name and number are on the AFIT website. If you just go under the AFIT Physics Department, and again, Major Dan Emmons, look me up. If you got other questions or want to chat outside of this, just send me an email, give me a call. and I'm happy to talk about this with you. So thank you again for this opportunity.
Yes. Thank you so much for presenting. That was really interesting. It's I never really knew that there was kind of a weather system beyond the atmosphere of Earth, especially how much it can affect GPS signals and things like that, as well as this kind of I never knew about coronal mass ejections either and how they can affect power grids. It was also
Yeah.
very interesting to learn about all the different types of fields that you've worked in within the Air Force, from studying specific types of lasers to even using them as directed energy weapons.
Yeah, thank you. And what one parting shot for me, if you like the whole coronal mass ejection and how something like that can impact us, look up the Carrington event. Right, this was in the 1800s, and if you want to know the worst that we've ever recorded, it's called the Carrington event. We hope that something like that doesn't happen again anytime soon. Right, that would be catastrophic. I'd say. Right, it would be huge. And so it was I think it was like 1850s. I could be getting the date wrong, but check that out. The Carrington event. Um, ooh, boy, that's bad, right? It was lighting telegraphs on fire because it induced those currents that were so big that it was actually like it produced so much current that the telegraphs and things like that were catching fire. So just imagine what that would do now, right? Not trying to scare you all, right? Just saying there is this interplay between us and the sun that we don't typically think about, but it can go very wrong.
Well, thank you so much
Okay.
for
Well,
presenting.
yep. Thank you again for having me, and I really appreciate it. And seriously, reach out to me if you guys have any other questions about anything. Okay. Thank you. I'm gonna go before my kids break something in here. Okay. Thanks, everybody.
Thank you so much.
Bye.
Thank you so much.
Thanks.
Please join us next time on December 4th for our next presenter, Francis Pierce, who is currently the 5G implementation team for Qualcomm. He's also helped design specialty test stations for 4G and patent pending for 5G design implementation. Day to day, he tests phone performance and makes sure that it works and runs according to design specifications. And he has been assigning tasks to tech staff as a technical manager since 2005.